So I have to do a little interest inventory with the students and see, what kind of interest they have. Good example, I know of a project many years ago, there was a girl in South Carolina that was an athlete. She was a volleyball player, a really good volleyball player, was going to play in college, but she didn't like science, didn't really have any idea what she wanted to do. So she told her teacher that she liked volleyball. Well, the teacher said, well, what are some things about volleyball, some questions you have? She said, well, one thing is when I serve, I hit the ball, sometimes I can't control where I hit it. Or if I hit it a different place on the ball, whether it's near the valve stem or whatever, I'm wondering which volleyball is truest, or is there one kind of volleyball that I could probably serve and be more consistent serving with than other kinds? So she actually developed, she was going to develop an experiment on testing which volleyball was the truest. And the teacher, when you hit it, you could depend on where it was going to hit on the floor. And the teacher said, well, you're going to have to develop some way to hit a volleyball. So she had to make a machine that was going to hit the volleyball the same every time, and she could change the angle, and then it might hit the volleyball 100 different times, and they'd hit it the same place on the volleyball, that particular brand, and then mark the floor where it landed. And then they might change it to another brand, hitting it exactly the same way 100 times. And so when it was all said and done, she got a 4-year scholarship because of her science fair project, not because of the volleyball scholarship. The volleyball manufacturers paid for her to go to college. I believe it was Voigt that paid for her to go. That was one of the truest volleyballs that she had. Anyway, but finding out what they're interested in and asking them questions and seeing what they want to explore. I guess we're up and ready to roll. Are we, Judy?
Yes.
Is that you?
Yeah, Judy is here. Judy, we cannot hear you yet.
All right, we could be looking at this slide though while we're waiting. The difference in the engineering process, the process you go through, you can handle it a very similar way. In science inquiry, you're going to be answering a question, and you're going to try to answer that question. We've been talking about questions. Engineering, you're going to try to solve a problem. So you're going to ask to identify some kind of problem. You're going to ask about that particular problem, what kind of constraints there are, what you're going to have to look at. One step the students like to skip is that second one on research. They need to find out what other people have done. If you're wanting to know which house is going to be easiest to heat, or which bridge is the strongest, or which tower is the strongest, or whatever your problem is you're trying to solve, they need to find out what other people have done. Otherwise, they might be copying that. And I can tell you, if they copy somebody else's design, that's just a verification experiment. That's not really an engineering project. They need to, and we'll show you a slide later, come up with something that's different. Is it going to be cheaper this way, or stronger, or easier to build? They're coming up with some way to answer a problem, but they need to find out how other people have addressed the problem. And then they're going to come up with possible solutions and imagine all the different ways. And they can't test everything, so that they might be able to test 2 or 3 different things. Then they're going to have to develop a plan for how they're going to, what they're going to measure, and how they're going to measure it, and how they're going to control things, very much like the scientific experiment. But they're going to test something. And ordinarily in a engineering project, they build a prototype. And we're going back to the houses we talked about a little while ago, about the garden on top. They might build models of lots of different houses. They got to make sure they're pretty accurate models and they're fair from one model to the next. And so they might build some type of prototype, and they're usually going to test it next. Is they're going to test that prototype, and let's say it's a bridge or a tower, they're going to test it till failure. So they shouldn't fall in love with their prototype, because they're going to break it. And they might have to build several prototypes just alike and keep testing them and changing things until they come up with what they want, their final model that they say they want to propose is this is a solution to the problem, and here's how it performs. So they're going to test things till failure, and they're going to improve them and redesign them and change them as needed. And sometimes that leads to another question. So it is a cycle. But that's the engineering process, and there's a link there that you can use that would help you. I'm going to go to the next slide. Are we able to do that? Yeah. Okay, so here's what we're going to do. Now I want you to, right now, I need to make a point. We are not solving a problem really with what we're getting ready to ask you to do. This is not a true engineering project. What we are trying to do is maybe showing how to work with a group of students. Students with engineering don't even know where to start sometimes. So I start with some simple things like this. We're going to build a tower, and in just building the tower and learning how to improve it, they learn some good building techniques. They learn how to think about variables that might be important, and it gets them thinking. So when they do come up with some type of prototype they're going to build to solve some problem, they can attack it better, the whole problem. So here's a mystery architecture, an activity we're going to try to do, and you're going to do this between today and next week, and really would like for you to do it by about noon on Monday of next week. So you need to finish this by noon on Monday of next week. We're not going to let you turn it in later like we did this time. We want to get the results soon enough we can incorporate them in what we're doing next week. So you're going to build, depending on your grade level, you're going to build a structure. You can see what 3rd through 5th will do, 6th through 8, and 9 through 12. And so in every case, you're building a tower. You could build it out of certain materials, which we'll tell you about later. And if you're 3rd through 5th grade, you're going to build the tallest tower using the materials we tell you that can support itself. It's freestanding. It cannot be attached to anything like the table or the floor or taped to it or anything. It's got to be like you could just pick it up and move it. It's freestanding, but it stands alone and it will stand up erect, and it's the tallest. And you'll just have to measure from the floor or the table, wherever it's sitting, to its highest point. If you're in middle school, 6 through 8, you're going to build the strongest tower that's at least 30 centimeters tall. So you're going to have to build a tower that's at least 30 centimeters tall. I would suggest you don't build it 60. You build it 31, and then you try to make it as strong as you can make it. Now, again, it has to be freestanding. You're limited to the materials we tell you. So using those materials, you're going to build the strongest tower you can that's at least 30 centimeters tall. We'll talk about how to measure strength in a minute. High school, you're also going to build a strong tower, but you're not going to be limited to height. Yours should be at least 40 centimeters tall, but you're going to get more. There's a formula here. You're going to get 1 point per gram you can support on top of your tower. We'll talk about how you measure that in a few minutes, but you're going to get 10 points for each centimeter tall. It also has to be freestanding, and you're going to measure it from where it sits, the floor of the table, to the lowest support. I'll talk about that in a minute, to the very top of the tower, but we're going to put a little piece of cardboard on top, and the lowest corner of that cardboard is going to be the height of your tower. So the cardboard should be horizontal. I'll show you that in a little bit. So you're going to measure from the floor to that's your height. You're going to get 10 points per centimeter. So if you build it 50, you're going to get more points. You're going to get at least 100 more points than if you build it 40, you'll get 400 points. If you build it 50, you'll get 500 points just for height. It says span, but that's not span, that's height. That last word on the slide should be centimeter height. But then if you put mass on top and it holds 400 grams before it breaks, you're going to get 400 points for the grams. So, okay, we can go on to the next one. They'll have the slide. Now, your homework is to take a photograph of the one you do build. Photograph it before you measure it or test it. Photograph it, because it might get damaged. If you're elementary, you'll send the photograph to me. If you're high school or middle school, you'll send the photograph to Judy. Try to get a good, clear photograph. Then you're going to test it. Elementary is just going to measure the height. You might even take a picture if you measure the height, with the tape up there. And then I'll talk about how you measure it, how you test it for weight in a little while. But you're going to have to share how your tower performed. You're going to be able to tell us, or you can tell us the data. And if it failed, I would like for you to explain where it broke. Like if you're doing middle or high, you're going to break it. You're going to add mass until it falls over or collapses. And you might go back and refer to your photograph and maybe tell where it broke or why it broke in certain places, why it failed. That's really the key to making a better one the next time, is to know where that one failed. And if your tower starts falling over elementary people, you'll know what's letting it fall over. You maybe decide what would keep it from falling over. How could you build it even taller with the same materials? Okay, let's go to the next one, Judy.
Yep.
That's okay. That's good.
We don't have your elementary ones. So here we go.
Well, elementary, they're just going to measure the height.
Right.
Elementary is easy. So here's what's going to happen. I'll show you a photograph in a minute. I got materials in front of me, but high school, middle school, you're going to cut a piece of cardboard, and we're going to have to, one thing we might not have done, Judy, is we might not have told everybody the size the cardboard needs to be. It needs to be the same size for everybody. Now, I got a piece of cardboard that's about 13 centimeters on the side. It might be better, let's say it's going to be 15. That's a nice number. So you're going to have to cut a piece of cardboard square, 15 centimeters on the side, exactly. No less, no more, as accurate as you can. And what you're going to do is, when you've finished your tower, that piece of cardboard cannot be taped or connected to your tower. It has to lay on top of your tower. So your tower has to hold it up, because the height's going to be measured from the bottom of the tower to the lowest corner of this piece of cardboard. And then you're going to put stuff on it, middle and high school. You're going to put things that have mass or weight on top. And you look, since you don't have the little masses that I use little masses that are easy, that are measured. They're either 5, 10, or 20 grams a piece. You don't have those. You're going to have to use things in your kitchen. You might put the cardboard on and put something that's not very heavy to start with, but you're going to have to find things in your cupboard that tell you the weight in grams. It's really mass, but they're going to tell you the ounces, and then they're going to tell you be converted to grams. In case you don't know, if it doesn't have the grams, 1 ounce is equal to 28 grams. And you're going to start with something small, and you can add mass to the cardboard, and you're allowed to touch your tower on the side just to steady it. But you've got to move your hands. If it falls over or collapses, you're done. So you can keep adding mass to the top, and you can take the light thing off and put something heavier, or you can put both things up there. But keep up with how much mass is on the top. Might even take a photo when it's all said and done of what was on top of the cardboard. And if it survives, you can add more to it. Keep increasing it until it fails. Okay, Judy, I think we can, and then they calculate their score. Elementary is just going to be measured to the height, and you can see how you measure the middle and high. And I keep mentioning the lowest corner, that piece of cardboard, the height's determined by the bottom of the tower straight up to the lowest corner of the cardboard is. And we're going to agree it's going to be 15 centimeters on the side. And again, you're going to analyze your failure to tell how you can make it stronger. And maybe next week when I see some of the photographs, I can tell you some techniques that you could use to make a stronger tower. But if the students do their research, they'll be able to research and find some techniques that are already in existence that make the tower stronger.
So Manley, there's a question about, is holding the most mass what determines the strongest tower?
Yes. And at high school, it's going to be a combination of most mass and height. So they have to make a decision. It has to at least be 40. Would it be better to have a tower that's 80 tall that can only hold 100 grams? Or is it better to have a tower that's only 50 tall that holds 1,000 grams? They're going to have to decide whether they want to do that. They might want to do like middle school. Middle school is building one that's 30, and then they're making it as strong as they can with the materials they have. High school could build one that's 40, and then they're going to make it as strong as they can with the materials they have. Or they can actually build it taller if they want to. It's got to be tall and strong if you're high school. Middle school, it's just got to hold up the most mass. So that's the answer, is yes, the most mass. Not a simple answer, because high school is a little different. Okay, Judy, I think we can go to the next slide.
Okay, I think the next slide is it.
Okay, all right. So that's the assignment. It's due by next Monday at noon. Here's the piece of cardboard, Judy. If they listen to me talk, they can see it. Here's my piece of cardboard. Just a piece of square cardboard. It's going to be 15 centimeters on a side, and then we'll tell you the materials. I think we don't have the materials in a slide somewhere, Judy.
I think that Teresa has sent that to them.
Yeah, I did send them. I will send them again, and I will update it to include that 15 centimeter measurement for you.
I use the string like it's yarn string, nothing heavy duty. It's not yarn or crocheting string or something like that. It's just the string you buy at a hobby shop. It's like kite string, works fine too. But here's a ball of string that they can use, and it tells you how much you can use. You can use popsicle sticks. It tells you how many you can have. You can use tape. I have the blue tape here. I like the blue tape because I can put it on and off the tape. And you're going to have straws. And the question you're going to have is, can we use the paper that comes off the straw? The answer is no. You have to use just the straw. And I have to tell you, McDonald's straws will give you an unfair advantage. So when we did this in class, everybody would have the same straws. Like paper towels, we don't always have the same at home. But if you can use McDonald's straws, they are usually stronger. We're talking about regular length. Hardee's has straws that have 2 lengths. We're not talking about the longest red straws they have. We're talking about the shorter red straws they have. That would be the regular length straw for Hardee's.
Yeah, not coffee stirrers, but straws.
Not coffee stirrers, but straws. And here's a clear straw. This one I bought in mass, but you might find these like somewhere else. I don't know where you'd find them, but Wendy's is going to have a different straw. All the different fast food places. McDonald's usually they have a bigger diameter and they're stronger. So that might give you a tip. But Teresa has told you how many to use.
But you can't cut them.
No? What, the straws?
Yes,
You can cut them once you get them. Once you're using them, you can cut them.
right. That's what I was saying. But you
Yeah.
can't use any more straws than what, or
That's
anything
what I
else.
said. Yeah.
given.
That's right. And you can use an index card. It tells you there you have an index card you're allowed to use. So, what the funny thing is, sometimes I use a piece of paper. I don't think that's on our list this time, but you have the materials. Let's build us a tower. If you got questions, you can ask me. Any questions about the tower building, even elementary, middle, or high can ask questions. Okay, Judy, that's it for tower building. And Teresa's going to send them what.
Okay. All right, so moving on, we now have an hour to cover in 30 minutes. So such is our life, right? That's the way it works.
32 minutes. Okay.
All right, so talking a little bit, let's go a little bit more about comparing that scientific method and engineering practices. Again, and Manley touched on this as well. Sciences, we're asking questions that were, that testable question, whereas the engineering, you're defining a problem or a need. You're developing and using models with the engineering, with the scientific, you're developing that investigation that you're going to be doing and planning it. With both, you have to analyze and interpret data. So you're using your mathematics, you're using your computational thinking, and you have to really, students have to learn to think beyond the box to be able to get to that plan and to get there. If you have mathematics teachers, this is a great time to bring them into the discussion on how to look at the data and how to represent data. So you're constructing those explanations and designing the solutions. With both, you have to come up with how you can argue what your evidence does. Putting together that conclusion of what you have gathered and being able to communicate it with other people is extremely important to do. So we decided, we switched this around a little bit because we wanted you to be able to do a research plan with an engineering project if you wanted to do that, not just the scientific. So looking at the important points to think about if it's the engineering project is you're making a case for something that we don't already have an answer to. We may have a way of doing something, but you think there needs to be a better way. So that is by all means acceptable of improving on what we already do. But again, you've got to do the background research so that you know what we do along the way. You've got to be able to compare it to what's already been done and how yours is different and better. So you're going to have to be able to determine what you're going to test, what you're going to measure, and how you're going to determine whether or not it's successful. And that's one of those constraints that we talk about in engineering is what parameters does it have to fit in order to feel like your model or your solution has been a success. And you do want to test it until it fails and then be able to look at it again, retest it, and maybe redesign. So some of the problems that people think about that are out there, that we may not be able to do as students or teachers, but they are engineering problems. The hurricane-proof houses, and they actually, when I was at ISEF one year, I had a student that won one of the large awards because she had redesigned windows in mobile homes to make them much more energy efficient. And she won a bunch of money for that one. And so that was an engineering problem. The bridge solutions that we have for Oregon Inlet, that's an engineering issue. And we're saying, you think about increasing the yield of a local crop. Is that scientific or is that engineering? It could go either way. It depends on what you're doing. If you're developing a better way of doing something you already do, then that's engineering. If you're going to be looking at growing it better or changing your fertilizer or something like that, then that's more the scientific. So I am going to be moving fast here. And I want you to think about your classroom activities and how you can actually make them into more engineering projects, because you may discover a lot of the things you do with your students, whether or not you realized it before, are really engineering type issues that you want to look at. So we're going to move on and we're going to talk about, if you are doing an engineering project, where do you start? And we talked about this with the scientific project. With this, you have to just, engineering, you've got a problem or a need or a goal, what you're working towards. You have to do that background research. You have to specify those requirements and constraints so you know it's going to be successful, or what is going to be considered this works. You need to brainstorm solutions, figure out which one is the best solution you've come up with, and you do the development work and to build that prototype. You analyze it, you test it, and then you redesign based on your analysis and your testing along the way. So when you get started with the scientific method, we've talked about getting that topic and then developing your testable question. With engineering, you have to find that need, something that meets a need that you have or another person has or a group of people or something else. There's a lot that's out that students can look at in the news, that they can look in their life around them, of ways to be able to improve things that can make, developing something that can make life easier for someone or better. To look at some of those unsolved problems or things that may have been solved, but in reality, they've been solved pretty poorly. That may be a better one. Once you've come up with that need, then you need to make it into a problem statement. This is like your testable question. So your problem statement needs to answer these three things. Sound familiar? What is that problem or need? Who has it? And why is it important to solve it along the way? Because who needs it? What is it? And why do we need to do that? And that's your problem statement. And that needs to go. And all of this, we haven't really talked about your journaling very much, but every time a student does anything, whether it's finding their topic, doing their background research, developing that testable question, with engineering, getting that need or the problem, developing that problem statement, all of this goes into that journal along the way. Bibliographies as well. So some examples of problem statements. Students need an easier way to lock their lockers at school because the combination locks are hard to unlock and often they get jammed. So they need to think about what's a better way of locking their lockers. That's the need. How can I go about developing something? And when we haven't, now it'd be like it's too hot to go outside. Instead of the bad weather, although we may have hurricanes coming the way it's been going lately. Dogs not wanting to go outside. How can you get around that? There are some solutions out there. Maybe we can come up with something better. And hopefully we'll have students in school at some point in time where we'll be talking about lunch boxes again in schools. So how can you keep them better space? So anyway, looking at your project, you want to be able to come up with a solution that is better than what already exists. And that's one of the issues that we have out there is we know about a lot of things, but it's not always the solution that is the best solution, but it's something that works. We have a young man that went and won at ISEF, and his younger brother took up the project, refined it, and got a whole lot better data, more intensive data, more sophisticated data in a research lab. Both of them won awards with it in looking at better ways to build wind turbines. and looking at blade morphology and ways of being able, one started with the shape of the blades and the other one went to looking at putting protuberances on the blade so that they caught more wind. And they won at the science fair, science and engineering fair level. They won at Student Academy of Science. They won at Junior Science and Humanities. And we're working doing internship at GE, where they build a lot of the wind turbines, and lo and behold, GE found somewhere in their archives that they had taken out a patent on doing this exact same thing that these young men were doing. So it was interesting the way that developed. But anyway, but you want to look at if it's doable. Can you design a solution that's safe to build, that you can use it? You want to know if you can get the access to materials and the equipment that you may need. Are you going to have time to be able to develop that? And that's something that you need to think about when you're putting your projects together. And that's why you really need to start working on these projects early in the year, so there's plenty of time to go through all the different steps. And you need to look and make sure that they meet the rules and requirements for science and engineering fairs. I will tell you that there are fewer regulations and rules about doing engineering projects, because most engineering projects don't work with animals. They don't work with hazardous biological materials. And if they have humans, it's humans testing something instead of humans being tested upon. So it's a lot easier with all the rules and regulations in some of the engineering projects. So when you're developing, you develop that problem statement that you have, and you look at what you're going to be doing, and you think about the prototype that you're going to build. You want to be looking at, how am I going to test that? All of this goes into that research planning that we're going to talk about some more next week. So how am I going to test it? How am I going to analyze it to be able to determine what would be the best prototype? And then I'm going to look at how am I going to validate my solution with users? Am I going to need to have test subjects to be able to look at it? In which case you will need to have the human subject form filled out, but it's not as bad as if you're actually testing the humans. And you need to be able to decide whether you need to redesign something. And that needs to come about from the testing that you do to see what are your possible failures, where are your weak points, what are things that you need to work on. How will you know if you succeeded? That goes back to being able to formulate the criteria and whether or not it meets the level of being successful. Manley, do you want to put anything in on this one while I'm talking?
No.
Okay. So looking at the project itself, I've talked about this some already. Every project is going to need a research plan that's written prior to the experimentation. Now, you're going to be doing this in your classroom, so you're going to be looking over things as students are developing it. But I will tell you that when we get projects at the regional level and even at the state level, it's pretty obvious that the research plan was written after they did whatever it was that they did, whether it's a scientific project or an engineering project, because everything is written in the past tense. And it's kind of hard when you write it before you do the experimentation to think about writing in past tense saying, I did such and such, when you haven't done it yet. So it's pretty easy for us to figure that one out. So it needs to be done beforehand. And teachers, I cannot stress how important that is for you to know what students are being engaged in, and and for you to review it and determine whether or not it is something that is safe for them, and if they have taken the precautions that are out there. If your students are working virtually, this is even more important for you to be able to say, this is the research plan, you are approved to do this. If you change anything, you have to get approval before you can move forward. And that is for your own protection. And that will stand up saying that, your parents have to approve this as well. So you've gotten approval by parents and approval by you, then you know you have to look at what they're doing, make sure it's being done safely. That engineering project you need to have in that research plan, you need to have that possible solution, how you're going to develop that solution, that method, what the constraints are, how you're going to test it. You also need to have within that, any of the safety issues that you need to address along the way. So, research plans. This is your other homework assignment for next week. So we needed to at least touch on it. So that's why I was running through the rest of it to be able to get to your research plan. And this can be a scientific project or it can be an engineering project. When you're looking at it, you need to think about, you got testable question or the engineering problem statement that you've come up with. Is it going to be worth your time doing it? Is it going to be original? If you can go on, I don't want students going to Google to get ideas for science projects, but if you as a teacher can take that question that they've developed and Google it, and you come up with exactly what the students has planned on doing, then it's not original. And you really need to suggest to them they do something a little bit different. Ask a different question, can be on the same topic, but change the variable that they're using. They need to change the project so that it's not exactly what's already been done. And then that's the next thing. Can it be done? Do they have access to materials? Can you help them get access? We have a group of students that work with a teacher in the Brevard County in North Carolina. They don't have a lot of scientific equipment for them to be able to use for the very sophisticated test, like in a research university, but they have developed networks in universities around the country that they have sent tests off to these other labs, and they have tested things for them for free. And so that will happen, that can happen. So even though you don't have the facilities, someone else may have it for you to be able to use. What materials are you going to be able to use? And again, are they available for you? What are the safety issues students are going to be working with? If elementary, you have to think about, okay, if they're going to build a structure for an engineering project and they're going to need to use a skill saw to cut the wood, that's a safety issue. So you're going to have to make sure that they have a parent who knows how to use a skill saw, not someone who's never seen one before, but someone who knows how to use it, or a guardian or another adult that can assist them with that so that it's not a safety issue for the student. So
or cut it for them. They can cut it for them. They aren't doing the project, but they might cut something for them.
Right. And there is actually a form that goes over a lot of that. And that's, if you look at the ISEF forms that I think we may have already sent out to you, the rules and regulations and forms, it's actually form 3, where it's a risk assessment form. And so this would be listed using a skill saw. That's a risk. So how are you safely going to address that risk? And it may be that someone cuts out the pieces for me that I've designed, or that I have someone who is assisting me, who has taught me how to use it and is there while I am using it. But those safety issues you need to address. How are you going to measure it? How are you going to test it? We talked about quantitative data where you actually get real numbers. Qualitative data is where you are putting in, this is what we are seeing, this is what it appears to be. In journals, we like to see both of those, but when you're testing something, you really need to have as much quantitative data as possible to be able to really be able to compare your results and your data. You need to think about where you're going to be doing the project. We may have more students doing projects at home this year than we've ever had before. So that we need to think about that, is who's going to be supervising the student, who's going to be working with them. And I'll remind you again, no bacteria can be cultured and grown at home, period. even when we have homeschools, special accommodations have to be made for bacteria cultures to be grown. We do not at home. I mean, they have to set up a room. Well, anyway, I could go into it if you know, but you need to look at what the requirements are for working with bacteria. No one can go in and out of that space. It can be done at school. It can be done in a university or laboratory setting, industrial setting, medical center, out in the field. This may be the year that students may do more farm projects or more plant projects because they're not as many risks. However, if they're working with animals, then they're going to have that approved by someone who is an expert on animal care and safety before they get started. Does it need a mentor? This is where we get into having someone supervising them, someone who knows more about those safety issues and can work with the student, or veterinarian who approves the project before it gets started, things like that. So getting local experts. So those are things that you need to think about before you ever get started. So one of the things that's going to be sent to you is a sheet that is actually the backside of the ICEF Form 1A. And it talks about how to do a research plan and all the steps in it. If you're elementary, you may look at that and kind of go, oh my gosh, there's a whole lot of writing on this page for my students. Well, you can simplify a lot of it. It really asks specific questions like, what is your question? What is if it's scientific, what's your hypothesis? And it has different sections. You don't have to address all of it, but it does tell you what you need to address if it's a human project. It tells you what you need to address if it's an engineering project or if you're working with animals or those types of things. That's why it's got so much information on it. It's a great guideline for you to use in developing your research plan. And it's a good one for you to work with your students to make it age appropriate for who you are working with. You need to have that timeline set up before you get started so students know what is going to be needed and for them to do and how long they have for each portion of it. In your research plan, you're going to say, I'm going to be testing something for, once a day for 15 days. So put how long you think this experiment is going to be lasting, how long, what that timeline is going to be for that research.
Maybe measure the height of the plant every day for 15 days, whatever.
Exactly. You're going to be writing your materials that you're going to need to be listed. And that can be a set one list. And that needs to be, depending upon who you are, if you're working with a more sophisticated project, that material list needs to be more detailed. If you have a student that is working with a cell line that they have obtained from Carolina Biological Supply, in testing something, then they need to say where it came from. And if they can go and get meat from the grocery store and test something with that, but then they need to say, this is my source, this is where it came from. So that that material list needs to be specific. Their methods and procedure need to go in there step by step, not written as a paragraph because that's hard to read, but written. Step 1, this is what I'm going to do. 2, I'm going to do this. Step 3, this is going to be next. This is a safety issue that I'm addressing from that one. So it is in a longitudinal order instead of in a paragraph. If they realize they need to change something, then they need to go back and revise that research plan and have it approved again by you or whoever needs to approve it. It's a human subject or an animal subject or a hazardous material, biological, someone else has to approve it because they may have changed it from being a safe experiment to being an unsafe experiment. So it's fine to change what they are doing, but if they do that, then it needs to be reapproved along the way. If they're building a model, again, it's the same way. If they readjust it, depends on what they're readjusting, if it has to go back for complete approval again. But being able to recognize what the safety issues and protocols they need to have in place is extremely important.
So Judy,
We're
there's
going-
a question. Do they need to be using the testable question they already turned in?
They can, but they do not have to. That's why we went over a little very quickly the engineering method, so that if they would prefer to do an engineering project, they are welcome to do so. So whatever you are interested in, please feel free to do it. Checking the ISEF rules to see if the project is allowed. I really encourage you to do that before a student ever gets started on something, because it's really bad when they have already done the project and then you come up and find out it's disqualified for competition because they weren't supposed to do that. When it could easily have been done a little bit differently and it would have been approved.
You're like doing an elementary project on germs or bacteria. You can't do it.
Right. And remember when I was talking about animals, you have to be careful about those. I remember one year, and this was probably about 4 years ago, 5 years ago, we had a student that had a really kind of cool project that they had looked at the effect of cigarette butts in bodies of water. And so they had set up several aquariums and they were putting cigarette butts in them. And they had aquatic plants in the aquariums, but they also put fish in there. Mm. And unfortunately, fish don't like cigarette butts. And the fish all died. And it was at a regional competition. And it actually made it to the state level. And everybody was talking about what a great project this was, this, that, and the other. And we looked at it and we said, you have to be disqualified because all of your fish died and you can't do that. And of course they were extremely upset, and we came back, and our goal is not to disqualify a student. Our goal is to get every student to compete and to be able to be excited about what they've done. And obviously they hadn't read the rules, but we said, if you'll go back and change your backboard, your display board, and just give us the plant material, because lo and behold, the plants didn't like cigarette butts either. So if they would take out every reference to any fish, because I think this was a middle school project, we would accept it as a middle school project. Just on the plants. Just Manley, I'm going to let you take over for a second. I've got a granddaughter here who's screaming.
Okay, that should have been counseled. That particular example should have had counseling earlier, maybe at the teacher level, said, look, you can't do something that's going to kill fish. They can't be involved. And then the project could have gone through even at the regional level. There was a mistake made in that example that Judy gave at the regional level, that they should have disqualified the project or had it changed at that level. So anyway, I'm getting ready to go to class, so Judy will hopefully come back in just a minute, but I think we're okay. Let's see if I can go forward on here. But now I do need to say something to the elementary people before I sign off. This can look like it's daunting and overwhelming and all that sort of thing. And really to everybody, we want to make sure that students are safe. And we've had a lot of questions that people have been asking about, how do you ensure the safety of the children? We need to know what they're doing. The teacher needs to be aware of what they're planning to do. And so that's the main reason for the forums, is to know what they're planning to do in advance. So you can tip off parents if they need help with things, make sure that the students don't get injured, or they don't do something that's going to disqualify them down the line, or they don't harm animals and vertebrates. Even if they're doing a project, middle school students love to do projects where they do a survey and they want to ask their friends what's their favorite cookie or whatever, or what's their favorite this or that. But if they do that, those are human subjects, and they have to get permission to use human subjects and fill out some additional forms. My advice ordinarily to elementary and middle people, don't do a survey where you have to use people. And that saves a lot of problems, a lot of paperwork. So Judy's back with us. Judy, I'm going to head to class, but
okay. All right. Sorry. When you've got a 6-year-old granddaughter in the next room and all of a sudden she starts screaming, Nana! over and over, you have to go find out what's going on.
That's laid plan.
Those are, parents and grandparents, you know what I mean. So anyway.
Yep.
All right. So I think we're down there. The end of my story is the parents came back and said, no, we paid to have this printed. We're not going to change our project and we won't compete. And I'm sitting here going, really? Because they had a very nice project.
All right, Judy, so we have 3 minutes to wrap up. I think you only have a couple slides.
Okay. All right, the Rules Wizard. And you'll be getting this presentation, but here it is in addition. This is on the ISEF website, the International Science and Engineering website. When you click on this link, it asks specific questions about what you are planning on doing. You need to answer the questions according to what you've developed for your research plan. You can do this after you've done your research plan, and you don't have to give me a 5-page research plan. You can give me in brief, what this step would be. You don't have to give me every detail about what a step would be. So I don't want this to be an onerous process for you along the way, but something that you can actually think what your students would be going through. But when you get through that research plan, go to the Rules Wizard, answer the questions, and at the end of the Rules Wizard, it will say, based on the answers to your questions, these are the forms that you will need to complete. We'll talk about these forms next week. We'll also talk about research plans, excuse me, because you're going to send your research plan in to me. So here is your homework. This is the last slide. You've got to complete that engineering build, send the photographs of it along with the data and the model that you have built. You've got to develop a research plan from your testable question or an engineering problem. You can get a completely different question if you would rather do something else. It does not have to be the one that you've done before, okay? It just needs to be something that you would be interested in spending the time working. If you're going to do a research plan, you might as well develop it with something you want to do. And you may notice that at the end of the research plan, you're supposed to list your bibliography. So you can make up some names of books if you want to, or you can give me some actual names of sources. You can list, like, make up a wildlife agent's name if that's who you're going to talk about, or an ag extension agent's name. Just tell me made up name, but ag extension agent. For your bibliography, remember your elementary, you only have to have a minimum of 3, but middle school and high school need a minimum of 5 to be able to do. Then once you get your research plan, do your Rules Wizard, and at the bottom of your research plan, tell me which forms it says you're going to need, because we're going to talk about them. And we will show you on next Tuesday a way of, if you have like hundreds of students in your school during research projects, or even if you have 30 students that you teach during research projects, a way of getting around having to do every single form right up front. You can do it develop an online format for them to be able to use. But if they go to a competition, like to a regional competition or a state competition, they have to then take the dates they have from when you approved it and when it was approved and put those on the official forms for us to be able to have. But that's the assignment for next week. And I think that's it. So there it is. And I'm only like 2 minutes over, even though I had to run out of the room. So any questions from anybody?
All right, so with that, if you do have questions, you can stick around, and Judy and I will hang out for just a couple minutes for questions if you are all set for the week. Oh, is your granddaughter okay?
Yes,
Answer that for the group.
Fine. She's 6 years old, and her major crisis is that she lost the link to the show that she wanted to watch, and she couldn't figure out how to But she was screaming my name like 6 or 7 times. I was going, oh my gosh, what's happened? You know, I could imagine a bee having gotten in and stung her or something like that. So, yeah, I went, okay. I think you're fine. We can figure this one out real quick. But I appreciate your concern. Thank you.
Yes, thank you. And I am going to just put a link from Twitter to the governor's announcement as they live tweeted it if you are looking for it. And I will send out the email with all of the documents from today. It's going to have lots of attachments. If you don't get it, then it got blocked by whatever server your email told us. So feel free to just reach out directly to me and I can send you an individual one that hopefully won't get blocked.
Right. Sometimes the blocking is when there are multiple people being emailed, the number of people that are in the email chain. But we can we'll hang out and say in case you have any questions.
Oh, thank you, Brad. Yes, there's a Plus Delta feedback form that I can drop into the chat link or chat window, and I will also include it in the email follow-up. We are distracted this afternoon. Okay, so thank you. If you don't have questions, you can jump off. I do see, it looks like Akira, is that how I say your name? Akira has a question. Akira, you can jump